Welcome back. You're now watching the second part of this online GPlates tutorial. Let's start with the answer to the question about plate convergence in the Pyrenees. To measure this in the most convenient way, the trick is to anchor Eurasia. So I'm going to anchor 301 because this way I can now very easily measure the distance between the present day location of Cadaqués and Cadaqués 121 million years ago, which is about 600 kilometers. So now we know that there was much more plate convergence than shortening. And I think this very nicely illustrates why it is important to make good plate reconstructions like this. If you would only study the rocks in the Pyrenees, you would think that Iberia moved to the north for only 100 to 150 kilometers. But thanks to the marine magnetic anomalies in the Bay of Biscay, we know that it must have been much more than that. So the difference between those two is subduction. There must have been quite a large basin here between Eurasia and Iberia. And that piece of plate, that piece of lithosphere has been lost. There's no rocks left of that in the rock record of the Pyrenees, which means that there's only one option. It must have disappeared into the mantle by subduction. Okay, that was to finish off the first part about Iberia. In that part, I've shown how GPlates uses Euler poles to create moving plates on your screen. But GPlates can also work the other way around. If you move a feature over the globe, then you can let GPlates calculate the Euler poles that are associated with that motion. I will illustrate this in the South Atlantic. I'm going to go to the present. So what we have here is two continents, Africa and South America, with the marine magnetic anomalies of the South Atlantic Ocean in between. So the pink anomalies are part of the South American plate, the orange ones are part of Africa. The spreading ridge is of course in between here. So we want to reconstruct South America with respect to Africa, which means that we're going to drag South America and keep Africa fixed. So step one is to anchor Africa again. At this point, as you can see, there is a South American plate in the GPML file, but it's not yet in the rotation file. And before we can start moving South America, we have to specify how we want GPlates to calculate the Euler poles for South America. And in this case, we want to let GPlates calculate those poles with respect to Africa. So I'm going to open my rotation file. And I'm going to add two lines in here. It doesn't really matter where you add those lines, but to keep the plate ideas in order, I'm going to put them here. South America is 201, and I'm going to add a line for the present, 701, and then an extra line. And the age of this line doesn't matter much, as long as everything that you want to do, every rotation that you want to calculate, is within that time interval. So for now I'm just going to choose 300 million years ago. Okay, save, close, and reload. There we go. Now GPlates knows that plate 201 exists, and it also knows that it should calculate the poles for 201 with respect to 701. And now we can start reconstructing. So the ages of those marine magnetic anomalies, they're given. If you select one, you can see the age over here. So the youngest one is 10.9 million years old. The youngest one on the other side, of course, has the same age. So both these anomalies formed at the ridge 10.9 million years ago, which means that at that time they were directly on top of each other. So what we can do is select the South American one, go to 10.9 million years ago, this should be, and then I click on this icon, which is the the dragging tool to make a reconstruction. And then you see that the entire South American plate is selected, because if you move one part of that plate, the rest of the plate moves with it, of course. So now I'm going to start dragging South America to place those 10.9 MA anomalies on top of each other. If you want to rotate, you have to hold Shift. I'm just going to search for the best fit. which is not always easy. Yep. Okay, so now I'm happy with my fit, and I'm going to click apply. So in this window you can check if you've done everything right. So you want the pole to be calculated for the age 10.9, 701 is fixed and 201 is moving. So that's all in order, okay. And now it's just a matter of repeating this for all the anomalies. So I'm going to check the age for the next one, 20.1. I'm going to select South America again and then drag until it fits. Okay, apply. Okay. I'm just going to repeat this for the rest of the anomalies. Okay, I've now done all anomalies. The last one, the oldest one, is 83 million years old. So if I now click play, we see the South Atlantic opening. So this is exactly what we want. So 83 million years ago, as you can see, Africa and South America are quite a bit closer together than they are today, but the South Atlantic Ocean is not yet fully closed. The problem is, as you can see, there are no anomalies older than 83 million years old. These marine magnetic anomalies, they are a record of the reversals of the Earth's magnetic field. So to make these anomalies, you need reversals, of course. And unfortunately for us, from approximately 120 to 83 million years ago, there were no reversals at all. This period is called the Cretaceous Normal Superchron. And I guess if you study the Earth's magnetic field, it may be a very interesting period in geological time, but when you're making plate reconstruction, it's just very inconvenient that there are no anomalies to work with. So even though we cannot make that part of the reconstruction, we do know that based on the geology of the continental margins of both Africa and South America, that the South Atlantic must have started opening around 130 million years ago. So what we can do is to make a fit of South Africa and of Africa and South America at 130 million years ago. So again, I'm going to drag South America and just make a nice fit of them. Something like that. Okay, so now we reconstructed the entire opening of the South Atlantic Ocean. And I'm just gonna run it, see if it looks good. If I'm happy with all of that, I'm going to save my reconstruction. So let's just run for a bit. Yep, looks good to me. So I'm going to manage feature collections, and then I'm going to save my rotation file. So now if I open my rotation file, you see that GPlates added all these lines. So the ages of the anomalies have now Euler poles that are the rotation of South America with respect to Africa. So we still have this 300 MA line with those zeros. We could delete that line, but on the other hand, what it does now is that if you go further back in time, you'll see that South America is moving back towards the present day position, because it should end up at those zeros again 300 million years ago. So that's not what we want, of course. We know that South America and Africa were both part of Pangea. They were stuck together for quite a long time. So what we actually want is that they stay in their 130 MA position when going back further in time. So I'm just going to copy the 130 pole and add it on this line like that. Save, reload, and now we have a Pangea fit in, well, 200, 230, and then after 130, the South Atlantic chute starts opening. Okay, that was all I wanted to show. I'm just gonna let it run one more time. Congrats on making your first reconstruction in GPlates. I hope you liked it, and I'll see you in class next week.